All right. So, guys, this chapter 14, I want you to know, first of all, that it is a standalone chapter, meaning it's not combined with any other chapter, okay? Chemical kinetics is a topic that I don't think any of your Chem 1 teachers would have taught any of the concepts, so like 95% of this chapter is going to be new to everybody, which sounds intimidating maybe, but for whatever reason, this chapter seems to connect with basically everybody. If you're a math inclined person, if you're more of a concept person, I will tell you that in years past, the test scores for this test are some of the highest of the whole year. I'm not saying it's easy, I'm just saying it just seems to click with people, which is great, okay? So, chemical kinetics, what does that mean, okay? This chapter is all about speeds, rates, how fast or how slow does a reaction occur. We've never talked about that before. I have asked you to predict whether a reaction is spontaneous or not, favored or not, but we've never talked about speed. And just because something is thermodynamically favored does not necessarily mean that it occurs quickly. Okay, some spontaneous reactions can take 10,000 years to be complete. Okay, but chemical kinetics means speeds, rates of reaction. Okay, and actually, let me go back. You know, if you think about those of you that are in physics or you've taken physics, you know, when you talk about rates and velocities of things that are, you know, moving objects, you have units of like meters per second. That's a really common unit for a speed or a velocity. Well, that's a distance per unit of time. How do you measure the speed of a chemical reaction? We're not measuring distances, we're measuring changes in concentration per some unit of time. Okay, so you'll see this kind of notation a lot. Delta, of course, means change. What do brackets mean? Concentration, molarity, okay? So changes in molarity over a change in time. Okay? That's how speeds are measured. Speed of a chemical reaction will be measured. This letter A, it could be a reactant, it could be a product. Okay? You can measure it from both sides. So I'm going to use this synthesis reaction as an example. Okay, I've shown that to you, that reaction to you before. That synthesis reaction, this is just sort of extra information, actually has a name. It's called the Haber process, H-A-B-E-R, Haber, that's a person's name. So synthesis of ammonia, the Haber process, I'm going to use that as my example. And if you look at this graph, okay, you've got time on the x, concentration, molarity on the y, and this line is showing you what happens to the concentration of one of the reactants, hydrogen, over time. Since it is a reactant, it should make sense to you that its concentration is decreasing over time. I mean, think about it. At the beginning of a reaction, you have a ton of reactants, and over time, they get consumed. Okay? Nitrogen, the other reactant, also decreasing over time. Okay? But I want you to look at this graph, look at the reaction as it's written up there, why is it that hydrogen is disappearing, decreasing its concentration faster than nitrogen? Anybody want to guess why? There you go. It's all to do with the coefficients, the molar ratio. For every 1 mole of nitrogen that is consumed, 3 moles of hydrogen will be consumed. Hydrogen should be disappearing faster because we're taking more away every time this reaction occurs. Okay. So my 2 reactants are in some ways disappearing over time. What's the opposite of disappearing? Appearing. That must be what's happening to the product, and it is. Okay? Over time, the concentration of your product is going to increase. Now, what's going on when all of these lines flatten out? What's happening? Yeah, we're at equilibrium. And just, I want you to remember once again that equilibrium does not mean that the concentrations of all my players here are equal. That's not what equilibrium means. Remember, equilibrium means the speed, the rate of the forward reaction is equal to the speed of the reverse. That's what's equal, not the concentrations. Okay? And we can put some numbers to this situation. Okay? This would be a perfect example of something you would likely see in multiple choice because it's relatively easy numbers that I would expect you to be able to work with in your head. It says if the rate of disappearance of nitrogen is 0.025 molarity per second. Get used to seeing units like this. This is what units of our rates will look like. Concentration per some unit of time. What is the rate of disappearance of hydrogen? Okay, we'll stop there. We'll do the other one in a second. Okay, if nitrogen is disappearing at this speed, what's the speed of the rate of disappearance of hydrogen? Can you do the math in your head? 0.075, yeah. Remember, hydrogen is disappearing 3 times faster. Well, what's 3 times 0.025? 0.075 molarity per second. Okay, it's just to do with the coefficients. How about the rate of appearance of my ammonia? We were given information about this guy. What's the number? Do the math in your head. 0.050. Yeah. Ammonia is appearing twice as fast as nitrogen is disappearing. Okay. So this would be just the rate here would be 0.075 molarity per second. The rate of appearance of ammonia would be 0.050 molarity per second. Okay. Very multiple choice kind of situation there. Right? Now, I said something to you last class just to kind of prepare you a little bit for this chapter. And I asked how many people in this class were taking calculus. Remember, AP Chemistry is not a calculus-based course. It's an algebra-based course. So I'm not going to teach any of this from a calculus perspective. But those of you that know calculus are going to see some connections. Okay? You're going to see some terms that maybe you see in your calc class. I'm not going to make those connections because I don't remember calculus at all. Okay? But you'll see some things that are a little bit familiar. So here's the situation, guys. This is a graph very much like what we were looking at a moment ago. We've got time, we have concentration of one of the reactants. It is decreasing over time. And we're measuring speeds, rates. And there's two types. Okay. I could ask you to tell me or calculate an average rate, like over the course of the first 5 minutes of a reaction, how long or how does the concentration change? Okay. It's how does the concentration change over a set period of time? In all honesty, we're not going to deal with this one very often, okay, if at all. We're not going to calculate average rates. We are going to focus on what's called an instantaneous rate, meaning not over the course of 5 minutes, but at this one particular moment. What is the speed? If we were going to do this graphically, okay, you would pick a point wherever whatever time they're asking you about, draw a line tangent to the curve, and you would do some trigonometry here to figure things out. We're not doing it that way, okay? That is one way to calculate an instantaneous rate. We're not doing it that way, okay? But the point here is, when I ask you to calculate a rate, I'm asking you for the speed at a very particular point in time, not over the course of some length of time. Okay? Now, here's the thing. We know reactions are reversible. Reactants form products. Products can form back into reactants. Okay? Until we reach equilibrium. But here's the deal, ladies and gentlemen. When I ask you something about the speed or the rate of a reaction, we want an instantaneous rate, and I don't want it at just any particular point. There is one place that we're going to be concerned with, and that is, what is the speed of the reaction the moment that it begins? Okay? Call it time 0. I have reactants A and B. At the moment that I mix them together and the reaction starts to go, that is when we want to calculate the rate. Okay? Okay, so we're going to look at the moment the reactants are mixed. Now, what does that mean to you? Why do you care? Well, guys, at the moment that a reaction begins, have we made any products yet? No, we haven't. At time 0, we have reactants only. So guess what? That means we are only going to care about the reactants. Okay. It's a process we're going to look at called the initial rate method. Initial rate meaning, what is the speed at time 0? And we will only focus on the reactants because we haven't made any products yet at time 0. So the very first thing you're going to be asked to do in this chapter, and it is very, very simple, is to write what's called a rate law. And let me show you what a rate law looks like. For this particular reaction, this is what a rate law looks like. Okay? If you come across a question that says determine the rate law, you're going to write something very similar to this. You're going to write the word rate equals K. That's a lowercase k, ladies and gentlemen. Make sure you take note of that. It's something called the rate constant. The reason I say make a special note that it is lowercase, what variable, what is it? A capitalized K in this class is a variable for what? Don't say Kelvin, that's a unit. Yeah, the equilibrium constant. Okay? Lowercase is a rate constant. Okay, what do brackets mean again? Concentration, molarity, okay, of my reactant here. If I had a second reactant, I would have another set of brackets being multiplied here. How come the products aren't part of this? Yeah, we haven't made any yet. We care about the rate at time 0. So when we write rate laws, ladies and gentlemen, it will include reactants only. When you're determining a rate law, really the only thing you have to actually figure out is this guy right there. That exponent is called the rate order. And you will need to come up with what is this number, okay? And that's the hard part. And it's not even hard. It's not hard at all, in fact. Okay? And I'm going to show you how you determine that exponent, okay? Now, there's a lot on this slide. Don't write it all down. Just don't. I'll summarize for you. 2 things to keep in mind. Number 1, we just said this. Rate laws will contain reactants only, no products. Okay. Products do not appear in the rate law. Why? Because we are concerned with the initial rate. There aren't any products yet. The second thing here, in order to find that exponent, you can't just look at the balanced equation. You must be given experimental data. And I'll show you what that looks like. Okay. Just a little vocabulary here before we look at a sample problem. Okay, calculus people, you might start to see some words that look familiar, like integral, integrated. Guys, just a little vocabulary here. There are 2 types of rate laws out there. This is the type we're going to look at today. We won't deal with this until class on Friday. We'll deal with that on Friday. This is the one we'll look at today. If you ever come across a problem that just says determine the rate law, they mean this first type, not this type. We're going to look at how do we come up with a differential rate law. And this is what the problems look like. I just talked about that. Here's what a problem would look like. All right, we've got a balanced equation. And as I said, we need experimental data in order to come up with those exponents. And here is what that data looks like. You've got 3 experiments. Here's my first reactant, and I've been given molarity values. Here's my other reactant, molarity values. And then this final column, those are rates, speeds. And it says, determine the rate law for this reaction. Okay. Well, here's what a simple rate law for this particular reaction is going to look like. I'm going to write the word. Rate equals lowercase k okay, the molarity of my first reactant, molarity of my second. And our job, ladies and gentlemen, is to figure out what are the exponents for each of those reactants. Okay? And here's how you do it. Here's the thought process. Let's start with this one, ammonium. We need to find the exponent for ammonium. And guys, I want you to think about this kind of like a science experiment. Okay? Think like simple, back to like 9th grade experimental design, okay? You are investigating how does the speed, the rate of the reaction, how is it affected when you change ammonium's concentration. Ammonium is like your independent variable. Rate is your dependent variable. Okay? Now, if you need to investigate how do changes in ammonium have an effect, what do you have to make sure about all other factors in your experiment? They're held constant. Okay. So let's focus in on ammonium. Can you show me or tell me which two lines I should compare where ammonium's molarity is changing, but everything else, meaning nitrite, is remaining constant? Which two lines? Okay, 2 and 3, sounds good. We'll compare these two lines. Well, ladies and gentlemen, please tell me, I use nice simple numbers. To get from point 1 to point 2, what do you multiply by? Okay, great. Stays constant, it has to. Can you do the math in your head? How do you get from here to here? What do you multiply by? 2 as well. Okay, so watch. Look at the numbers I just wrote down. 2 and 2, right? 2 to what power equals 2? You got it. Guess what? The exponent for ammonium is 1. Which, since it's an exponent of 1, you can either write it in or not, your choice. Okay? I'll go ahead and write it in. Good job. Let's look at the other reactant. Okay? Now this one is my independent variable. So I need this one to change, but I need all else, my other reactants, to remain constant. Which two lines should I compare here? 1 and 2, sounds good. Stays constant, has to. What's happening from here to here? Times 2. And what's happening to the rate? Also times 2. So once again, 2 to what power equals 2? It's 1 again. Congratulations, you just figured out your very first rate law. That is the answer. Okay? Now, let me give you some hypothetical situations, and I realize that the numbers will not reflect this, but just go with me on this. What if this is multiplied by 2, but from this number to this number, it's multiplied by 4? Your exponent is 2. Okay. This is multiplied by 2, this is multiplied by 8. Your exponent is a 3. Okay. How about, and I know this is not what the numbers show, this is multiplied by 3, because it doesn't always have to be increments of 2. This is multiplied by 9. Your exponent is 2. Okay. One final situation. This is multiplied by 4, and the rate doesn't change, meaning it's multiplied by 1. Your exponent would be 0. In case you haven't noticed, guys, your exponents will be whole numbers. 0, 1, 2, 3. Okay. Now, in the real world, do exponents that are not whole numbers exist? Yes, but you will not be presented with a problem like that. So let's say you come across a situation where this is multiplied by 4 and this is multiplied by 11. Yuck. 4 to the x equals 11. It's not that that doesn't exist in the real world, but you're not going to have problems like that. Okay? And that's it. Want to try one on your own? Not hard. Okay? Oh, sorry. Before we do that, okay, let me give you some more kind of sample questions that you might see. And guys, I'm going to tell you these questions, and you're not going to believe me that the AP exam would put something so easy on there. You won't believe me, but it will. Okay, you will see questions like this. Here's a rate law. They've given it to you. You didn't have to solve for it. There it is. And the question says, what is the order of the hydrogen ion reactant? It's the answer. 2. You don't believe me, do you? That they would put a question that simple. But they're testing you. Do you know what the word order means? And if it's helpful for you, put in your notes in like big capital letters. Order equals exponent. And if you were saying it out loud, this is how you would phrase it. You would say, the hydrogen ion is a second order reactant. Iodide is a third order reactant. This thing, which I don't know the name of, some kind of acid, this is a first order reactant. If you're ever asked, what is the overall reaction order? All I am doing is adding up the exponents. Overall, this is a sixth order reaction. Okay. You try this one on your own. This last part here, if you have an idea on how you might solve that last particular question, go for it. If you're not sure, you're welcome to just wait and we'll talk about it. Try this. Okay. Questions about just that part? Are we okay? Okay. But let's look at the last part to this question. Okay? We got the rate law, we know the overall, and then it says, what is the value of the rate constant? Meaning, they want an actual number for K. Anybody have any ideas what you might do? Plug in what? From which line? Okay, she's right. Pick any line you want. I always pick the first line just because that's just what I do, but you can pick any line you want, plug in the values into the rate law that we just found, and solve for K. Now, if you choose a different line than I did, will you get a different value for K? It might be slightly different, but for the most part, these values for K, depending on which line you pick, should be pretty much the same. I'm going to just pick the first line because that's just what I do. Someone this morning asked a good question. Does the rate constant, what we just solved for, K, does it have units? Yes, it does. We'll get into that in just a second, okay? All right, I want to give you one more to practice. It says write the rate law expression. That means come up with the rate law. What is the overall reaction order, and what is the value of the rate constant? You now know how to do all three of those things. Let's do it. Guys, let me just interrupt you here for 1 second, just in case this was causing a problem for anyone. When you're trying to find the exponent for this first reactant here, which which two lines look to you like the best ones to compare? To find the exponent for x. Okay, well, hold on. The one that you're focusing on needs to be changing, and anything else has to stay constant. Okay, it can't be 2 and 4.
Oh.
This one has to be changing, and this one's staying constant. 2 and 4, that's not going to work. This isn't changing. So 3 and 4. Okay. Now, to get from here to here, what are you multiplying by? 1/2. Okay, fine. Staying constant, it has to. What are you multiplying to get from here to here, approximately? 1/4. Okay, well, we can work with that. I mean, 1/2 to what exponent, what power equals 1/4? 2. Well, guys, here's the reason I'm bringing this up. If those fractions bother you, okay, you don't like fractions, I don't like fractions, just look at it going the other direction. You don't have to go top to bottom. You can go, what's happening from here to here? It's being multiplied by 2, being multiplied by 4. If that makes you more comfortable, then do it. Doesn't matter. Keep going. Okay, how'd you do? I rounded this to 2 significant figures. I think it was like 10.6 or something. Okay. So let's talk about units, because yes, this does have units. And here's the bad news, although it's really not that bad. The units for the rate constant are different for every problem. Ugh. Well, let's figure out how to deal with this, and then you'll realize it's really not that bad. Okay? I'm going to look at my rate law again here. And what I'm going to do, in order to find the units for K, ladies and gentlemen, what I'm going to do is rewrite this rate law. But instead of using variables, I'm going to use the units for the things that I do know. For example, all rates, okay, no matter what problem you're given, rates always have the same kind of units. Rate constant has different units for every problem, but rate will always be measured in some concentration per time. Okay? So instead of writing the word rate, I'm going to write the unit. And I'm going to write it like this: molarity per, and I'm just going to use the generic word time. It could be seconds, minutes, hours, fortnights, whatever. Okay? Molarity per time. Okay, equals. I don't know the units for K, so I'm going to leave that as a variable. What do brackets mean? Molarity. Okay? This molarity is being squared, and then there's another one next to it to the first power. I'm just going to simplify that a little bit. Let's make the right-hand side molarity to the third power. You with me? You okay with that so far? Okay. Think basic algebra, ladies and gentlemen. How do you isolate K? All right, divide both sides by molarity to the third power. Gone, canceled out. Can I simplify this a little bit? What can I cancel out here? Okay, one of the molarities, this exponent becomes a 2. All right, now, this looks really messy, so let's clean it up a little bit. In this particular problem, the units for K, I'm going to write it 4 different ways. And all 4 of these are acceptable. It is totally your preference. here's the first way I could write the units. This is a little bit of a clunkier way, but it works. 1 over time over molarity squared. It's a little clunky, but it works. Okay, maybe I write the units like this. 1 over time times molarity squared. That's fine. If you want to make it look a little cleaner, maybe you write it like this. Or if you want to be really slick, maybe you write it like this. Ladies and gentlemen, all 4 of these are exactly the same thing. It is your preference. Okay? I'm typically going to write it like this. So I'm going to now take that unit and I'm going to attach it to that number. Now, here's a little trick. The overall reaction order was 3, right? Your units, are you listening? This is a shortcut, which you can memorize, but I would prefer that you didn't. Your units for K, and this works every time, will always be molarity to the negative 1 number less times the inverse time. Always. So let's say the overall reaction order is 6. What are the units going to be? Molarity to the negative 5th times time to the negative 1st. What if the overall reaction order is 1? Molarity to the negative 0? Yeah. Anything to the 0 power is just 1. So the units for K in that situation would just be inverse time. That's it. Okay. All right. The last thing that I want to do today is I want to give you some assistance with one of your problem set problems. You should have a book in front of you. We're in chapter 14. Please go to where the chapter 14 problems are. This is number 38, which is one of your problem set problems. All right. Now, before I start this, okay, this is another very similar situation. You know, we have this chart of data. We're going to come up with a rate law. There's a little twist to this question, which is why I want to do it with you, so that you don't go home and you get to this problem and you're super confused and throw your hands up and, you know, rage quit and flip the table over. That would be terrible. Okay? But let me just say, the little twist that comes into this problem, you definitely need to know how to do it. Are you getting that? Okay. Laying it on pretty thick. I'm not being real subtle here. Okay, so let's look at this one. We've got an equation, all right? We have a table of data very much like what we've been looking at. We've got molarities of our first reactant, molarities of our second, we have rates. And the very first part says, determine the rate law. Okay, no big deal. Before you even look at the chart, we're going to start writing it out. Rate equals first reactant, second reactant. Our job is to come up with those exponents. Okay, fine. One reactant at a time. Let's deal with this guy first. Which two lines should we compare? 1 and 2. Okay, sounds good. Okay, now you may be able to do this in your head, you may not. From here to there. And you know what, if you're not sure? What if you're not sure? To get from there to there, it's being multiplied by what? I don't know. What do you do? How about this number divided by that number? Tell me what you get. It's not 1/3. 1.5. Okay. Staying constant, it has to. Guys, make life easy on yourself. Both of these have times 10 to the 6th, so just ignore the times 10 to the 6th. What's 3.9 divided by 2.6? Also 1.5. So what's my exponent for this reactant? 1. Okay, great. Now let's figure out this one. Let me erase that, sorry. In order to find the exponent for this guy, which two lines should we compare? What's the problem? Yeah, there's no place, there's no two lines where my other reactant remains constant, and we gotta have that. That's why we're doing this problem, okay? Because what do you do in this situation? You can't just use, okay, well, this is this and this is it. You can't do that. So there's something else you have to do if you come across this special circumstance, which you will, okay? So what do you do? All right, well, I minus is the one is like my unknown. I don't know what the exponent is for this guy. So pick for me, ladies and gentlemen, two lines where I minus is changing, and I don't care what the other reactant is doing. 1 and 3, fine. Okay? 1 and 3. Sounds good. Well, what I'm going to do is I'm going to come over to this rate law that I know some of it. I know some parts of it. And I'm going to look at line 1. And I'm going to enter the numbers that go for line 1. Line 1, rate. 2.6 times 10 to the negative 6th. I don't know what K is, so I'm going to leave it as a variable. On line 1, this molarity is 0.018, and I know with confidence that that is to the first power. That I am sure of. The other one, I don't know what the exponent is. I'm going to call it x, because I don't know. Let's fill in the same thing, but this time from line number 3. The rate on line number 3 and it's to the x power again, because I don't know what the exponent is. What are we going to do with all of this? I'm going to take these two lines and I'm going to treat it like a gigantic fraction, which looks horrible, but actually it's really, really simple. If this is a gigantic fraction, does anything jump out at you right away that I can cancel out? Yeah, K, gone. Gone. Okay, keep it simple. One piece divided by one piece, and even make it simpler than that. Get rid of the times 10 to the 6th. Tell me, please, what is 2.6 divided by 7.8? 1/3, so 0.333. Okay, equals, what's 0.018 divided by 0.036? You can probably do that in your head. 0.5? What's 0.036 divided by 0.054? What is it? 0.6666 to the x power. Okay. Now, people, don't flip out. Don't think, oh, unknown exponent, are we going to have to like do logarithms and stuff? No. No. Divide both sides. What's 1/3 divided by 1/2? Give me a decimal. What do we get? 0.666, repeating, equals. What is x? 1. We had to do all of that just to find out that that exponent is a 1. Now guys, remember what I said. In these problems that you are presented with, the exponents are going to be whole numbers. Okay? So, you know, what if you saw this? Yeah. Even if you look at that and you say, well, I'm not really sure, this has to be a whole number. It's not 1. What is it? Try 2. Is it 2? It's 2. Okay. All right. Now, let me make sure you guys are aware of something. Your textbook, meaning the solution manual to your textbook, likes to do this method for all of these compare line by line problems. I find that to be a little bit of overkill. Okay? Most of the problems we've done today, ladies and gentlemen, we didn't have to do all of this. Okay? The only reason I have took you through this process is because for this reactant, we could not find 2 lines where this guy changed and he stayed constant. Okay? Now, here's the bad news. Are you ready? You're on your own for the rest of this. All I helped you do was just the first part of part A. Okay? Determine the rate law, we now have it. Okay. But you can handle the rest. That is where we will stop today.